Look up at the night sky. What do you see? Countless tiny sparks of light. These are stars. Each one is a colossal sphere of superheated gas, mostly hydrogen and helium. Our own sun is a star. It's the source of all our light and warmth. Stars are fundamental components of the universe, born from vast clouds of gas and dust. They live for millions or even billions of years, generating energy through nuclear fusion. This process releases an incredible amount of energy, which is why stars shine so brightly. Imagine a furnace so large it dwarfs planets, so powerful it can be seen across unimaginable distances. The light from the nearest star beyond our sun, Proxima Centauri, takes over 4 years to reach us. So when you gaze at the stars, remember you are looking at gigantic, distant suns. Each one has its own story, life cycle, and destiny. They are the crucibles where the elements that make up you, me, and everything around us were forged. Understanding stars is key to understanding our universe, our origins, and perhaps even our future. Stars are not just pretty lights. They are the engines driving the cosmos. They are the reason we exist. Stars are much more than just beautiful celestial objects twinkling in the night. They are the architects of cosmic structure and the engines of galactic evolution. Galaxies, like our own Milky Way, are vast collections of stars, sometimes numbering in the hundreds of billions. These stars, along with their planetary systems, gas and dust, are held together by gravity. In the fiery hearts of stars, nuclear fusion reactions convert simple elements like hydrogen and helium into heavier elements. When massive stars end their lives in spectacular explosions, they scatter these newly forged elements across space. The iron in your blood, the calcium in your bones, the oxygen you breathe, all these atoms were cooked up inside stars. We are, quite literally, made of stardust. Stars serve as cosmic lighthouses, allowing us to measure vast distances and map the universe. Their study continues to reveal the universe's grandeur. Stars are born, live, and eventually die. The birthplace of stars is within enormous, cold, dark clouds of gas and dust, known as molecular clouds or stellar nurseries. Within these cosmic cradles, gravity begins its patient work, slowly pulling together denser regions of gas and dust. As these regions contract, they begin to fragment into smaller clumps. Each clump is a potential protostar, the embryonic stage of a star. Gravity continues to squeeze these clumps, causing them to shrink and become denser. As a clump collapses, the material at its center heats up due to the conversion of gravitational potential energy into thermal energy. This warming, contracting core is called a protostar. Protostars are often shrouded by the remaining gas and dust of their parent cloud, making them difficult to observe in visible light. Astronomers use infrared and radio telescopes to peer through these dusty veils. Not all the material in a molecular cloud ends up in stars. Some of it might form planets, asteroids, or comets around those young stars. These stellar nurseries are dynamic, chaotic environments where the cycle of cosmic matter continues. The journey from a protostar to a true star culminates in the ignition of nuclear fusion in its core. As the protostar continues to contract under gravity, its central temperature and pressure build relentlessly. Eventually, the core becomes so hot and dense that a critical threshold is reached. At temperatures around 10 to 15 million degrees Celsius, hydrogen nuclei begin to fuse together to form helium nuclei. This process releases an enormous amount of energy. This energy pushes outward, creating a pressure that counteracts the inward pull of gravity. Once nuclear fusion ignites and hydrostatic equilibrium is established, the contracting protostar becomes a stable, shining star. It enters the longest phase of its life, known as the main sequence. The star will now spend billions of years steadily converting hydrogen into helium in its core. The birth of a star transforms a dark, cold clump of gas into a brilliant beacon of light and energy. The universe has just welcomed a new radiant member. Once a star ignites hydrogen fusion in its core, it settles into a long and relatively stable period of its life known as the main sequence. This is where most stars, including our Sun, spend the vast majority of their existence. During this phase, the star is in a delicate balance. The outward pressure generated by the heat from nuclear fusion perfectly counteracts the inward pull of gravity. The duration a star spends on the main sequence depends critically on its mass. More massive stars have much hotter cores and burn through their hydrogen fuel at a prodigious rate. Consequently, they have shorter lifespans on the main sequence. Less massive stars, like red dwarfs, burn their fuel much more slowly and can remain on the main sequence for trillions of years. Our Sun, a medium-mass star, is expected to spend about 10 billion years on the main sequence. It's currently about halfway through this phase. During its time on the main sequence, a star's primary activity is converting hydrogen into helium in its core. This process is incredibly efficient at producing energy, which is then radiated outwards. The universe is filled with an astonishing variety of stars, differing in size, temperature, brightness, and color. Astronomers classify stars based on their spectral characteristics, which are primarily determined by their surface temperature and their luminosity. The most common classification system is the Morgan-Keenan, or MK system, which uses letters O, B, A, F, G, K, M from hottest to coolest. Our Sun is a G-type star, often called a yellow dwarf. O-type stars are the hottest and most massive, appearing blue and incredibly luminous. They live fast and die young. M-type stars, commonly known as red dwarfs, are the coolest, smallest, and least massive stars. They are also the most common type of star in the Milky Way galaxy. Red dwarfs are incredibly long-lived, sipping their hydrogen fuel so slowly that they can shine for trillions of years. As stars exhaust the hydrogen fuel in their cores, they leave the main sequence and can become giants or supergiants. There are also more exotic types of stars, often representing the end stages of stellar evolution. This stellar zoo showcases the incredible physics at play across the cosmos. For stars like our Sun, the main sequence phase, while long, is not infinite. Eventually, the hydrogen fuel in the star's core begins to run out. With less hydrogen to fuse into helium, the energy production in the core decreases. Gravity starts to win the battle against outward pressure, causing the core to contract and heat up. As the core contracts and heats, the hydrogen fusion ignites in a shell surrounding the now helium-rich core. This shell fusion generates even more energy than the core fusion did during the main sequence. This increased energy output pushes the star's outer layers dramatically outward, becoming a red giant. Its surface cools as it expands, giving it a reddish hue. When our Sun becomes a red giant, it will swell to engulf the orbits of Mercury, Venus, and possibly even Earth. The Sun's luminosity will increase significantly, making Earth's surface uninhabitable long before it is physically consumed. Inside the red giant, the helium core continues to contract and heat up. If the star is massive enough, the core temperature and pressure will eventually become high enough to ignite helium fusion. While lower-mass stars like our Sun end their lives relatively gently, the most massive stars meet a far more spectacular and violent demise. After exhausting hydrogen and then helium in their cores, these behemoths continue to fuse progressively heavier elements, carbon to neon, oxygen, silicon, and finally iron. Each stage of fusion occurs in shells around the core, like layers of an onion. Iron is a cosmic dead end for fusion. Fusing iron nuclei does not release energy. It actually consumes energy. Once the core of a massive star becomes predominantly iron, it can no longer generate outward pressure through fusion to counteract gravity. The core collapses catastrophically in a matter of seconds. This rapid collapse triggers an immense shockwave that blasts the star's outer layers into space in a titanic explosion known as a Type II supernova. A supernova is one of the most energetic events in the universe. The explosion scatters all the heavy elements forged within the star throughout interstellar space. These elements, including everything heavier than iron, are created in the intense heat and pressure of the supernova itself. Supernovae are crucial for the chemical evolution of the universe. What remains after a star has lived its life and shed its outer layers, or exploded in a supernova? The answer depends on the star's initial mass. For stars like our Sun, After the red giant phase and the shedding of its outer layers as a beautiful planetary nebula, the core collapses into a very dense, hot object called a white dwarf. A white dwarf is about the size of Earth but can contain up to 1.4 times the mass of the Sun. It no longer produces energy through fusion, slowly cooling and fading over billions of years into a cold, dark black dwarf. For more massive stars that explode as supernovae, the core collapse can result in an even more exotic remnant, a neutron star. If the collapsing core has a mass between about 1.4 and 3 times that of the Sun, the protons and electrons are crushed together to form neutrons. This creates an object so dense that a teaspoonful of neutron star material would weigh billions of tons on Earth. Neutron stars are typically only about 10 to 20 kilometers, 6 to 12 miles, in diameter. If the core of the collapsing massive star is even more massive, greater than about 3 times the mass of the Sun, gravity overwhelms all other forces, forming a black hole. Black holes are the ultimate cosmic ghosts, warping space-time around them and profoundly influencing their galactic neighborhoods.